When I interview students and postdocs in my group, I tell them, I think the most important characteristic is that you should be motivated. Motivation is more important than what you know now. Because if you have motivation, you can learn things there. There was a paper in Science, they used a very interesting material that made the skin of the mouse transparent for a short period of time, so they could actually send the light into the system. It's quite fascinating. In other words, temporarily you can make some opaque material transparent. It's important that you be in love with the idea. And when you are in love with the idea, you can learn, you can be motivated, you work hard, and you enjoy it. After all, you should enjoy what you do. I mean, that's what really matters. I always tell this to my colleagues, that we are very lucky. We are in a profession that we love what we do, and we enjoy it. That's an amazing thing.
In this episode of the 632 Nanometer podcast, the team is visited by UPenn Professor Nader Engheta, a trailblazer in metamaterials, nanophotonics, and electromagnetics. Engheta is a master of manipulating light and electromagnetic waves, pioneering a range of innovations from near-zero index metamaterials to bio-inspired polarization-sensitive cameras. He's earned accolades such as the Benjamin Franklin Medal and the IEEE Pioneer Award for work that has transformative implications in imaging, communications, and potentially even computing. This is a special episode for the hosts of 632 Nanometers. Xinghui and Misha grew up in the field of photonics, so to speak, following Professor Engheta's work, and Michael spent 4 years working on optical computing, which is Engheta's recent research interest. They discuss his fascinating journey through electromagnetics and his approach to finding new research problems. Engheta also explores the intersection of optics and artificial intelligence, discussing the potential for massively parallelized photonic computation.
Thank you, Nader, for joining us this morning on a Saturday. Very honored to have you here. Just starting with a warm-up question. If you were a high schooler, we would probably ask, what's your favorite color? But since you're a distinguished professor of electromagnetism, what's your favorite wavelength range? What's your favorite wavelength?
Or frequency.
Well, very good. First of all, let me say good morning to all of you. I want to thank all of you, Misha, Xinghui, and Mike, for your kind invitation. It's great to be here. I know all of you, and it's a pleasure to have to spend some time together. Now, back to your question. My favorite wavelength is yellow light. And so I like the color yellow, as you mentioned, but also I like microwave wavelength. And I worked in these two regimes, and I like infrared as well. But yes, if I were to pick a color, I would say yellow.
So like 590? Okay. Going to a little bit more serious notes. If we go back to the past, what brought you to the field of electromagnetics or to this wavelength?
To answer that question, let me take you back to my graduate student days. I got my bachelor's degree from University of Tehran in 1978. I came to the United States and went to Caltech for my graduate studies. So at Caltech, my PhD supervisor was Professor Charles Pappas, who was an internationally renowned scientist in electromagnetics, and I was interested to work in his group. And the first project he suggested to me was to explore how Doppler effect behaves in the near field of an antenna. So that was the first project he suggested, and I became interested in antennas. And by the way, that project led to my first publication. In 1980, IEEE Transaction on Antennas and Propagation, that was my first paper, together with one of his postdocs and himself. So I got interested in antenna and electromagnetic theory, and I became interested also in electromagnetic scattering from geological surfaces, because Professor Pappas had a grant from Jet Propulsion Laboratory at that time. Space shuttle, the first space shuttle was flown, and so there was a lot of interest in scattering from Earth and so on. I got interested in that, and so I did my PhD dissertation on interfacial antennas. These are antennas at the boundary between two media, and that was a hot topic in those days because of that was at the beginning of the monolithic microwave integrated circuits, known as MMIC technology at that time. So after I finished my PhD, I stayed with him one more year as a postdoc to finish things, and then I worked in industry for 4 years. Some of you did not know that, yes, because
Right.
I've been in academia since 1987. But between 1983 to 1987, I worked in industry. And in that industry, we were interested in electromagnetic pulse interaction with electronics and with materials. So towards the end of...
Is that a defense use case?
It was, yeah, at that time it was a little company. It's called Dykwood Corporation. It doesn't exist anymore. And it was part of Command Sciences Corporation. And they were interested in EMP. They called it electromagnetic pulse in those days. And towards the end of my PhD and during this time, I became interested in interaction of electromagnetic with materials, particularly chiral materials. Now, Professor Pappas had a very interesting paper several years earlier, before I joined his group, with one of his earlier students, about electromagnetic interaction with chiral structure. So I became very interested in interaction of electromagnetics with geometry and with chirality. So I became interested in that. So during that period, after a PhD, before I started my academic career, I published 2 papers with other co-authors on chirality. And when I came to University of Pennsylvania as an assistant professor in 1987, I started my group in microwave chirality. That's why I was interested in microwave. And in those days, we were interested to see how we can actually have chirality in the microwave domain. Because in optical domain, optical activity was well known going back to the time of Louis Pasteur in the 19th century. So we wanted to see how microwave chirality worked. And that's how actually I got interested in artificially engineered materials.
By the way, those papers saved a lot of my understanding during my PhD. I read all of them.
Thank you. I remember
the notation from it.
Yeah,
yes.
exactly. And so that was very exciting time. And this type of topics in those days, we call it complex material, which was basically precursor to what later on was called metamaterials, effectively is artificially engineered materials. So I'm getting to the point that you're saying is that in 1992, with one of my PhD students at that time, Mamdouh Sadoun, we introduced the concept of omega medium. Some of you may be familiar with that. This was just basically an interesting structure that you have something like an omega, letter omega in Greek, and that would be the inclusions that we consider that. And that material later on, after year 2000, become also an important material as far as the negative refraction is concerned later on. So that's my journey of how I got interested in interaction with materials. And in those days, we call it complex media or artificial material. And later on, that evolved into what is now known as metamaterials with different properties, so on and so forth. So I've always been interested, by the way, in interaction of electromagnetics, regardless of the wavelength, and the geometry. And chirality was a good platform for that, and also other properties of material. Index of refraction is one of them. And then later on in 2006, we had ENZ and supercoupling effect in epsilon near zero materials and so on. And then one thing led to the other. And I have to say, by the way, that you may know my work in metamaterials, but I've done also work completely different than metamaterials. For example, for several years, I work in bio-inspired imaging that's inspired by eyes of some animal species who can actually see polarization of light. Because I became interested in biology of visual system. I went into that field, introduced some imaging system that we built camera system that could see the world with that type of property. This inspired by the neural system of these animal species that can see polarization of light.
So you were building polarization cameras then?
Yes, we did that.
Wow.
Oh yeah.
That's very cool.
did that. We had several patents on it. So that had nothing to do with metamaterial. But it's interesting because my interest in interaction with materials started in microwave, as I mentioned. But a natural question you may have in your mind is, how did I get into nanophotonics from that wavelength to this wavelength? And the intermediate region was my interest in these eyes of animal species. Can see polarization of light. Because of that.
How do animals see polarization? What's the...
Very interesting point. Many invertebrates, bees, ants, octopus, marine, some of the marine species can actually see, quote unquote, see polarization of light, kind of analogous to the way we see color, so to speak. So their photoreceptors actually is evolved differently than photoreceptors in human eyes, and in general, photoreceptors in vertebrates, different than the one in invertebrates. So their photoreceptors, the molecules of visual pigments in their photoreceptors, actually, they have a specific order rather than being randomly oriented. And as a result, they can actually distinguish the orientation of the electric field when it goes into that. So essentially, think about an optical fiber that actually can have polarization sensitivity. But more important than that is how their neural system actually take advantage of this information and combine them. And that's something that, inspired us to look at something which we call it polarization difference imaging. Because if you look at the scene and at every pixel you pick up the image of the two polarization, if you add them up, of course, that becomes intensity image that we all do. But if you subtract them, what would you see? And that's how actually we build that camera, which was inspired by them.
Did you have a specific application in mind?
Yes. Several applications we had in mind. The first one, by the way, was inspired by nature again. And although some of these marine species, by the way, can see polarization of light, why? What advantage do they have? Of course, biologists and zoologists have discovered how these species can see that. So that's in their domain. But what we were interested is to see that, okay, for example, they can see farther away. So can that polarization help them to see farther away? The answer is yes. So we wanted to see whether if we build the camera ourselves, because our eyes, human eyes, are polarization blind. Effectively, we cannot detect polarization. But their eyes can. So if we equip camera with that type of property, can we do it? So that's what we did. We did that, and actually we did the experiment in my lab back in 1990s, almost 30 years ago. And we showed that, yes, if you do that, you can actually see farther away.
Oh, wow.
For example, we had a tank of water. We put a little bit of milk in it. Milk is a very good scatterer. We build the target, put it there, and we shine light, just regular light. It wasn't, laser or anything, just regular light bulb. Light from here. From this side, we put the camera, we put the polarizer, we take series of images, and then we do post-processing with this methodology that's inspired by the neural system the species had, and then we saw actually things that ordinary eyes could not see.
So how far can you see?
Almost factor of 3.
Oh, wow.
Yeah.
That is amazing.
Factor of 3. And that became actually basis behind seeing through scattering media. It could be applicable to seeing through fogs. And we did it for water, but yes, similarly.
What's the mechanism?
The mechanism, good question, Mike, is the mechanism basically is removing the clutter. See, in a scattering media in water, there's a lot of scattering. Those scatterings have certain polarization properties, particularly if the light coming from the top. That's usually, for marine species, that's the case. So the light that's coming towards the observer has certain polarization. Whereas when you put a target there, the polarization coming from the target has a different orientation than that. So by doing this differencing, you can actually remove the clutter.
Ah, interesting.
And you can see farther away.
It removes randomly polarized light.
It removes, I wouldn't call it completely randomly. In our experiment was randomly, that's true. But in the actual marine species, because the light is usually coming from the top, the polarization actually is partially polarized. But it has a specific orientation because the light coming from the top. So if the target has other polarization, by removing the background, the other one will show up. Yes. So that led actually to other interesting applications. For example, we were able to distinguish between different shadows. It's very interesting, by the way. If you look at an urban area, there's a lot of shadows. Those shadows also still have some photons coming to the imaging system.
Oh, it's like from the Brewster angle, or is it different?
It's a different one because of orientation of the angle of light that's coming. So, for example, if there is a shadow that's coming from two buildings, there's a shadow is shadow. But the one that's coming from this building has different polarization properties than the one coming from the other one. And that could distinguish. But perhaps the most intriguing application.
Wait, sorry, I have to. So if there's a shadow, the light is hitting the building and it's not going through. So the shadow is an absence of light.
Yes, but it's not completely absent. There's still some photons there.
Is that from the backside of the building?
Yes.
I see.
Yeah, exactly. Or some diffraction that happens from there. So there's still, because if it's absolutely no photon, then of course you have nothing.
No polarization.
That's exactly right. But perhaps one of the most intriguing applications that serendipitously we came across that is that we could detect the fingerprints non-invasively. It's very interesting.
Oh, that's very interesting.
Yeah, and this came to me completely serendipitously. I was reading some papers from biologists who were studying the polarization vision of certain class of insects known as the water bug. And there is some technical term for that. I don't remember it right now. And these water bugs, by the way, when they want to land on the surface of the water, they tilt their body with a specific angle. And from that, they recognize this is a flat surface, and it's a flat surface of the water, not any other liquid. How do they do it? Brewster angle. So they actually do the Brewster angle, and from that, they actually dive into that. So we said, this is very interesting. You can actually recognize the flat surface. So I went to the lab. By then, we already had the polarization camera. So what would happen if you actually put something on top of a flat surface? So we got a CD cover, and we said, put the fingerprint, said, can we detect that? And we were able to detect that with our camera system, and that actually became a technology there. Anyway, so that has nothing to do with metamaterial, but what happens is that actually got me into the visible light from microwave. And I said, okay, very good. Now my interests in microwave are complex material, or artificially engineered material, now with the light. Why don't we actually combine that? So that's how I went to the shorter and shorter wavelengths, and eventually to nanophotonics, photonics, and nanoscale optics. So that's how the journey works out. And sometimes, as we all experience in science, serendipity takes you from one place to another.
Oh, absolutely. That's super interesting. So did this then turn into a product that people were using for fingerprint recognition?
It was interesting. Not directly that application, but we had several patents on that. And a company was formed, not by me, by someone from the business school at the university, a graduate from business school at the University of Pennsylvania. And actually, a company would move to California. This is back in 1990s. But unfortunately, the owner of the company eventually, passed away, and that company was dissolved. But yes, at some point, they were very interested in the camera aspect of that, particularly for flight and so on. The fingerprint one, no, as far as I know, that actually stopped there. But there was an interesting journey that we had.
You were just mentioning epsilon near zero materials.
Yeah.
I'm actually curious to hear, how did your thought process go around that? Did you just think, for instance, Veselago was thinking about, what if we had negative refractive index? Were you wondering what happens if it were close to zero? Or where did this idea come from?
Very good point. I'm always interested, by the way, in curiosity-driven questions. First, maybe even no application in mind, but just curiosity. What if question? I like to say it. What if question? Why not questions? So at the early part of the decade of 2000, there was a lot of interest in negative index, as you mentioned. And the idea was that, okay, can we actually make a material that have that properties? But of course, natural question is that, okay, if we can make a material to have negative index, could we make a material to have other interesting properties? And particularly for the epsilon near zero is that, as you know, in epsilon near zero, the index becomes zero, so the wavelength would stretch. So a what if question came to my mind was this one. Okay, if I have two waveguides, and I want to connect these two waveguides in a very arbitrary way. Obviously, if I send the mode from here, it's going to reflect part of it, and part of it will go through. What if I put some material with epsilon near zero in that region? Now, why was I thinking like that? Was that, okay, just curiosity, purely. I didn't have any application in mind. So I said, if epsilon, we know that epsilon equal to zero would give you the wavelength very long. So in that case, at the beginning of this material to the end of that material, the phase is the same. So if the phase is the same, what happens to the output of this material? So the same field that I have over here has the same phase over here. And if that's the case, do I get some form of tunneling? Okay, I didn't have the answer. It was just a thought process. I had some intuition. But at the same time, there was another intuition I had which was giving me the opposite answer. For example, if epsilon is near zero, the square root of mu over epsilon would be very high. So at the boundary between this part of the waveguide and this medium, you have a huge impedance mismatch. If you have a huge impedance mismatch, then what would happen to the field? Maybe the reflection coefficient is 1 and we have no field inside. If a phase is uniform, what good does it do if the field is zero? So these two intuition in my head was floating around. At this time, Mario Silverino, who is now is one of the prominent scientists in our field, at that time, he just was a young faculty in University of Coimbra in Portugal. And I'd known Mario since he was a PhD student in Lisbon. He wrote to me, he said he would like to come to my group for his sabbatical. I said, sure. I knew him. He was a brilliant student, but now he's a young faculty. He was a young faculty at that time. So he came to my group and I suggested this problem. I said, Mario, I have this question in my head. What would happen if we put this one there? And I told him the two intuitions that I had. And he got interested. He said, well, let's do it. I said, if you're interested, let's do it. So we started working on this, and we got lucky because we were able to solve that problem exactly analytically. And we showed that indeed it was very counterintuitive what we had in mind. Meaning that if you actually have these two waveguides and with the epsilon near zero in between, and when you make this region narrower and narrower, the wave actually tunnels through that better and better. It was very counterintuitive. At first, when we had that, we said, how could it be? We double check, triple check, everything,
Yes.
completely satisfy Maxwell's equation, everything. I said, this is amazing. So I said, Mario, let's do some simulation. This was interesting. Analytical result came first before
yes.
simulation.
That's-
So I said, let's do simulation. We did the simulation, we drew the material. It worked exactly at omega p. Drew the
Right.
plasma frequency. This tunneling will go to simulation. So we said, this is what it is. And then we tried to actually intuitively explain that using the transmission line analogy. Again, coming from microwave, that I felt more at ease with that comparison. And we said, yes, that's the reason it happens. We published that paper. It came out PRB 2006. And that's one of the highest cited paper we had there. And then 2 years later, we did the experimental verification of that. And it worked.
Wow.
And that actually launched a new field of near zero index photonics.
Yeah, actually, I've always been fascinated by the coaxial cables. I'm more like studied on the optic side, and I would assume that the optical waveguides should be half of the wavelength in the size. But then, if you take the coaxial cables, they are so small in the diameter, but the wavelengths are huge.
Exactly.
Is ENZ there partially, or?
No, it's not. Actually, it's a different phenomenon. That's a very good point, by the way. The coaxial cable, the reason you can do that is because there is one conductor within another conductor. And when you have one conductor within another conductor, the guided mode can have a zero cutoff. In other words, there's a mode with zero cutoff. In other words, you can say DC signal too, as we all know, DC. ENZ, no, it's not like that at all. ENZ is that the wavelength stretches. So for that particular frequency, and by the way, ENZ is a dispersive property. It's a function of frequency, whereas the coaxial cable is not. So ENZ, at that particular frequency, or the neighborhood of that frequency, the wavelength stretches. And because the wavelength stretches, essentially anything you put in that material looks small compared to the wavelength. Now, as you know, in electromagnetics, we always deal with the size of the structure compared to the wavelength. And the scattering depends on that, and all of the properties depends on that. Then basically, a consequence of the ENZ property is this. Okay, if everything is compared with the wavelength, what would happen if we stretch the wavelength? And how do you stretch the wavelength? You have an ENZ material. So if you put the object inside the ENZ material, that object, even though physically could be a sizable object, compared to the wavelength in that medium, looks small. That's why it has a lot of different properties. That's what the things can tunnel through this. That's what the scattering. That's actually related to the cloaking work that we did.
I think I represent the many people out there who are less knowledgeable about like
Sure.
ENZ and negative refractive index and so on. So maybe just I can ask some basic questions because I think for Xinghui and Misha, it's like this, they grew up on this. So, but basically, okay, so what does it really mean to have a negative refractive index material or an epsilon near zero? Practically, what does it mean, and how is it realized in a physical way?
Yeah. Okay,
because
very good.
I think probably 90% of the listeners, even if they're scientists, probably will have this question. So.
Absolutely. Great question, Mike. Yeah. In fact, in my class, sometimes I explain it to the students who are new in this field like this. So let me explain it, by the way, in a mechanical sense. Probably it's more related. Imagine that you have a mass and you have a spring. And you hold the spring over here. And imagine you move this one slowly. So obviously mass would follow the motion of your hand. Now imagine you gradually increase the frequency. When you gradually increase the frequency, this, of course, we have certain oscillation per second. This mass also would follow that. But there's also an inertia. And because of the spring, it goes, up and down, goes like this. So imagine you increase this, and then this mass would fall behind. You may get to a point that when these things go up and down, it's actually go the opposite of each other. There would be a frequency for which that would happen. So essentially at that point, you would say, okay, if that's the case, I have something that, this mass is going up and this one is going down, even though when the low frequency was that this would be following there. That actually explained how, for example, an electron polarization in a material will work, depending on the frequency of the wave that you have. If your frequency of the wave is low enough, the electron can follow the electric field that way. But if the frequency is high enough, electron will fall behind, kind of like this. So as a result, the polarization that contributes to the effective permittivity of the material would follow this. So you can have a scenario that this goes opposite to that. That can give you, for example, at a certain frequency, effectively zero epsilon. Remember, the permittivity is defined by having the original epsilon naught, or the vacuum, plus the polarization that happens inside. So how that polarization actually phase in and phase out with respect to electric field, that determine the value of epsilon. So at that particular frequency, you can basically essentially think about it, that what the dipole moment of the electrons would form would be opposite to the electric field that goes
cancels it out.
Effectively. And that actually, by the way, became the foundation behind our cloaking. When we did cloaking back in 2005, we were saying that if I have an object, and this has certain scattering because it induces dipole moment over here. If I put a material around it, naturally you would think that if I put a material around it, it would scatter more naturally. But that depends how that dipole moment is generated in that material. If that material is such a way that with the incident frequency, the dipole moment would be opposite, can it actually reduce the scattering? And we showed that it can.
And in the case of the epsilon near zero materials, how do you build a material like that? What does it mean to have a...
Very good point, very good point. Inspired by this issue that I mentioned, think about this. Almost any material that has this, well, you can do it two ways. One is if you have molecules and the electrons, of course, are basically pulled by the nucleus there. So there is that oscillation there, and that's the Lorentzian oscillation that you have there. If you pass the resonance, there is always a point that the zero crossing. That's one way. But the better way probably is just look at the free electrons material, metals. You just look at the metal. You have a lot of free electrons there. So those free electrons that goes up and down, they have a plasma frequency. And the plasma frequency is a frequency for which this zero crossing happens. So yes, you have a material. In fact, that's what we were proposing, that if you have a small sphere, let's say, for sake of simplicity, and you put a layer of a plasmonic material, which has that, then the polarization of that could be opposite to this, and that may give rise to the lower scattering that things happen.
At the plasmon resonance.
Or around that, yes. Depending, of course, on the size and so on in that case. For epsilon near zero, yes, at the plasma frequency. But for the cloaking, you need to go a little bit more in order to make sure that polarization cancels out.
So this was about epsilon permittivity, but also what about permeability?
Permeability.
For magnetic response.
Permeability, similar things. The physics of the problem is analogous to that, although I have to say that the permittivity is quote-unquote easier to deal with because you have electric charges, but you don't have magnetic charges. So in order to deal equivalently, you have to have loop of current. That's what you have. You have to have magnetic dipole moments. And some materials do have that you can deal with that. In other words, you can magnetize them, but many materials don't. So many materials are non-magnetic, whereas every material you pick up, you have some electric properties there. So in that sense, is more accessible to do it with permittivity.
So those omega unit cells, like the resonators, do they have that negative permittivity and negative permeability?
It could, yeah, exactly, yes, yeah. So that's one of the things, because if you look at looking at chiral structure, the chiral structure was the little helix, and you're very familiar with that thing, little stem and with the helix. And what happens is that when you have a stem and you have a helix, when the electric field comes, it excites the current along the stem, and this current also goes through the loop. So when it goes through the loop, you also have a magnetic dipole moment. So there's an interesting relation between, and that's the chiral media are all about. What we suggested is that, okay, if I get this loop and I turn it around, so you have something like omega, what interesting can happen? Because this dipole current will go like this, but the current in the loop would be that. So magnetic dipole moment would be normal to this. By the way, the first thing came to my mind back then in 1992 when my graduate student on the board, we were thinking about, we were not thinking about this way to see what interesting index would have. The reason we were thinking about that is to make it flat in order to have it easily can be made, because chiral is three-dimensional.
Metasurface.
Exactly. We didn't call it metasurface in those days, but what we were saying is that would it be interesting that rather than having something three-dimensional inclusion, to have a flat inclusion? Again, purely came out as a curiosity-driven question. What would happen? And one thing led to the other. In fact, one of the early applications we were thinking about was the phase shifter in a waveguide, because in a waveguide, electric field and magnetic field are normal to each other. So if you can have this omega structure, its magnetic field would be in the direction of magnetic dipole and electric field. Coming back to E and Z, just basically a curiosity question on the waveguides to see what that thing leads. And that's what I tell my students, just be courageous asking this what if question, why not question. You never know. During my career, and I've been in the university for 37 years, often these type of questions led us to interesting domains.
Was that also what compelled you to go back to academia after having worked in industry for 4 years?
Absolutely,
to be able to ask these
absolutely.
what if questions?
In fact, I went to industry with the knowledge that this is not my career.
Right.
I mean, it was a good experience. I'm really thankful to my colleagues and friends that I made during those 4 years in industry. But I knew from the beginning that my career would be in academia. So that was a good detour at that time. And I tell my students, sometimes you have to take those detours. You'd like to get to your goal, but maybe the path is not just straight. Sometimes you have to take a detour. At the time that you take that detour, you say, okay, no, that was my goal, but I have to do this. Well, I tell them, several years in the future, you look back and you say, actually, you're glad you did that because you learned something new. And I tell you, that's exactly right. I mean, I learned actually a good amount of electronics when I went to that company. As a graduate student, I took a lot of physics courses, a lot of engineering, electrical engineering courses. But in that company, I learned, how electromagnetic interacts with electronics. And that actually helped. And later on in my academic career, that actually helped me to bring the concept of optics and electronics together using optical metatronics.
I seem to remember that you also conveyed an anecdote where one of the first projects you worked on was to build an antenna or design an antenna for an airplane. Was that something that...
Well, yeah. So here's an interesting point, by the way. I think I know which episode you're referring to. As I mentioned, my first research project was in antennas. Doppler in the near field. So I became fascinated with antennas. But antennas actually can teach you a lot of interesting physics. And one aspect of the antenna is this. If I have an antenna, usually antenna is not just up in air. It's connected to something because you have to feed it or you have to get a signal out of it. So where do you put the antenna? Near what? Usually the object that you put it nearby is metallic. Airplane, ship, buildings, maybe
phones. No,
I'm sorry. What?
Phones. We had
phones.
in our previous
phones.
episode
Yes, that's right.
with Eli Bonovich, where he mentioned about that Apple disaster.
Exactly. But in those days, by the way, of course, we didn't have cell phone. But yes, you're right. So what happens is that if I have a simple dipole antenna and I want to put it near a plate, let's say an airplane or something, how do you put it? So you say, okay, I put it like this. So let's say you have a plate and you make a hole on it and you bring a coaxial cable and you connect the external conductor to the metal and the internal conductor coming out, and that becomes your antenna. Very simple. The problem is that antenna that's coming out, in order to be a good radiator, should be normal to the interface. Why? Because if you have an antenna near a perfect conductor or good conductor, radiation, it would be equivalent of that antenna, its image. And if I have an antenna like this, its image of that is like this, and these would be in phase. And that antenna radiates well. Okay, very good. That's one of the reasons old-fashioned radio stations that you see, they have an antenna long compared to the ground that you have. But in airplane, the designer would not allow you to have antenna sticking out because hydrodynamic of that was very hard. So obviously you would like to have an antenna be conformal. So I say, okay, I don't like this antenna. Nobody would allow you to have an antenna like this on the airplane. So you have to bend it. The problem is if you do it, then the image would be like this. And that antenna would be a very poor antenna.
Do you need like a magnetic mirror?
Exactly.
No?
That's exactly right. And back then we were working actually, we didn't call it metasurface, by the way. We called it high impedance surfaces, HIS. There are different terminology we were using in those days, or we call it AMC, artificial magnetic conductor. In optics, and we were not in optics in those days. I was not in optics. In optics, they used to call it magnetic mirror.
Yeah, PEC, PMC?
PCP. No, PEC, PMC is a very formal definition of that. But even technologically, it was called magnetic mirror and so on. Later on, when metasurface became very popular, several groups did magnetic mirror. In those days, we did it, by the way, with designing, because after all, there is a ground plane. You cannot have something without a metal. So how do you make something near a metal being artificial magnetic conductor? And one way we did that is that you have a very thin dielectric, and on top of that, you design a patterned surface. We never called the word metasurface, but that was metasurface. A patterned surface such that when you send a wave to this reflected wave, which has a magnitude 1, because of course there's a conductor on it, the phase of that becomes 0 rather than 180. Because for the perfect electric conductor, the phase is 180. But for perfect magnetic conductor, the phase is 0. So that was an interesting engineering concept. And for that, if you put an antenna parallel to that, it radiates. But there's a catch. The catch there is the bandwidth is very narrow. So there's always a catch.
Can we see those antennas on the planes?
Well, I don't know. Right now, of course, much more sophisticated than that. There's a lot of composites and so on they do. But this was one of the interesting research topics in those days, and several groups were working on that. How to actually have an antenna near a conductor. And it could be for other applications, not just airplane. But it's interesting.
All right. Since we touched the base on Metatronics.
Metatronics, yeah.
All right.
Sure. Go. Okay.
We keep interrupting your next
before the antenna thing, but it's good. That was interesting. These are just things that came up when you were talking. So one is, if you could today, had zero responsibilities, like a young man, right?
Sure.
No students, no citations.
No grants.
No grants, no citations. If you were going to do another 4-year stint in the industry, if you could get a job at any company, where would you work?
Good question. If we rewind the time to that one, I would say Bell Laboratory.
Yes.
That's fine.
A good point. I would say maybe places that they're looking to the future. I think maybe Apple and Google, particularly because of all these aspects of artificial intelligence that's going on, which is quite fascinating. And I can touch upon that later on in our discussion, that I think photonics can play a fantastic role there, by the way. I think in my personal opinion, is a golden opportunity that photonics can do. That's one of the reasons, by the way, that's one of the reasons I think studying some of the aspects of optics in computing could be useful. Yes, it has its own limitation, no question about it, and we'll talk about it as we go through this. But I think the whole concept of computing is coming back. And artificial intelligence has been around, as by the way. The reason it's become a lot of discussion about it now is because our computing platform has come to a point that can do tremendous amount of data and analysis, but still, there's a lot of room for improvement that needs to be done. So yes, Mike, to answer your question, if I were a young man and I was at the beginning of my career and you say I didn't have to worry about grant and so on, I would say I would like to actually see, I love optics, so definitely, again, I would go into optics. But how to actually apply optics, I would say definitely artificial intelligence is one aspect of that. Another one is also biology. I think that's another interesting point because biology is a complex system. I am very much in favor of optics always. I think optics can play a very important role there. And in fact, several groups already showing that, like optogenetics things that's going on. It's fantastic. And also, in some sense, if you think about it, artificial intelligence relates to the biology because it's inspired by that. So I think optics can play a very important role in these two aspects. So I tell young students that you're in a good time. It's good that you're at the beginning of your career because there's a lot of exciting things going on.
Yeah. Especially, I think, like for the companies like Neuralink, when they show that they can use like what is called, they put essentially an antenna with connected to the brain, and then with the brain, you like without any hands, you can move the cursor on the screen.
Absolutely, yes. I mean, I think
it sounds like magic to me.
I recently tried one of these headsets. It's like it costs $1,500, and you put it on your head. It's like a consumer product. And it has an app, and it calibrates for a very long time. There's electrodes. You have to put water on the electrodes. It's like a very complex system.
Brainwaves?
Yeah, it's supposed to be measuring. It's like an EKG.
Okay.
I see, sure.
But you have to like really squeeze it on your head because it has to get through your hair, so you have to like, compress
Sure,
the hair.
sure.
And then eventually it's supposed to do something. But honestly, I felt nothing. So I complained to the person, I met the woman who made it. And I told her, like, look, I need to feel like it should at least be the equivalent of something like coffee or nicotine. I should feel something, right?
Sure.
And she's like, well, it's shown to be 10%, like in a study, 10% more focus, whatever.
I see.
So I think there's...
Massage the skull.
I don't know. I just feel like I wonder if there's been like good fundamental work on how to actually collect the electromagnetic, because it's a electromagnetic sensor, right? That's collecting this EKG data. And I wonder if there's been good work about how to collect it through, because the calibration process to get this thing to agree that it was connected was maybe like 15 minutes. Just messing around with it and pushing it. But it's like, okay, you're at 70% there, but then this kind of thing. And so I wonder how much kind of like fundamental, because you reminded me of this with the antenna. Like, I wonder how much fundamental work has been done to make that connection.
Sure. I don't know about in that field now, but I tell you my own experience there several years ago. I mentioned about this getting into polarization vision of eyes of animal species and so on. In that, I had a very good collaborator in the Department of Psychology at the University of Pennsylvania, Professor Edward Pugh, who is now at the University of California, Davis. And I learned a lot from him, by the way. He's a neuroscientist, and with regard to the aspects of photoreceptors of eyes and so on. So during that collaboration I had with him, after we studied actually it's interesting how I got interested into that field, because one day I got a phone call. I was just a young associate professor, maybe 4 years I've been at the University of Pennsylvania, early 1990s. I got a phone call from this professor. I had heard his name, but I didn't know him at that time. He said, I was referred to you that you are in the field of electromagnetics and optics, and I have a few questions on optical fibers. Can we get together? I said, sure. I didn't know why somebody in the Department of Psychology is interested in optical fiber. So we made an appointment. I went to his office, and he showed me a picture that he had taken through the optical microscope of the cross-section of the retina of a class of fish known as green sunfish. And he said there's some hypothesis that this fish can see polarization of light. And that's how actually I got into that field, because of his question. And then we joined forces. We started studying some of this photoreceptor of this species, and one thing led to the physics of the problem, meaning how to do the imaging. Anyway, that story I mentioned. But as our collaboration went on, Pew mentioned that I'm very interested in finding what you were mentioning, how the electric current in the brain works. So he explained to me, and I said, this is interesting. It's just like almost a DC, or very, very low frequency electromagnetics. He said, are you interested that we can actually teach a course in that field? I said, sure, but I'm not in cognitive neuroscience. He said, no, I need your knowledge in electromagnetics and how the current in the conductive medium. Essentially, that's what it was.
Then we brainetics.
Exactly. So what happened was that, sure enough, we wrote a proposal to the provost office of University of Pennsylvania to actually create a new course, which was going undergraduate, senior level, maybe early graduate level. And we did it. We actually had a course called Laboratory of Cognitive Neuroscience. We jointly taught that course for 3 years, 4 years, and then he moved to University of California, Davis, for family reason. And there, by the way, we actually studying, believe it or not, how actually the current in the brain behave from the point of view of electromagnetism. I was in charge of the electromagnetic part of it, and he was in charge of the cognitive aspect of that. And by the way, that reminded me what you said very nicely, is that when we were doing these things, because it was laboratory, so I actually had a lab, put it like this, you had to actually, to make every electrode, you had to put specific fluid there in order to make sure that the impedance would be low. Because the impedance of the skin and skull is rather high. So actually the person has to actually shampoo his hair first to make sure the oil is removed, because oil would cause high impedance. So you don't get that signal that nicely. Anyway, but yes, that's actually a very interesting area of science. Now, when I look back, I think optics can also play a very important role. We didn't do anything with optics with that project, but optics can play a very important role.
In what sense?
In the sense of getting the signal into the system. One of the interesting points, by the way, about the system is that because there's a lot of scattering happening, the penetration depth is not that much. But as you know, there's a lot of work going on. For example, Professor Hugh Cal from Yale University has done a beautiful job as to how actually send the light through scattering media and to focus something. That's a beautiful development that she's been doing. So one natural question comes up is that can those type of techniques of light scattering through the turbid medium can actually help us in biology? And I'm sure there is a way. I mean, she's expert in that, to do that. So yes, with all the knowledge that we are having in development in the optics in different materials, I have no doubt that that can play a role in that type of aspect.
What if you had some type of, for example, if you had a tattoo on your skin in certain places with some nanoparticles or something that improve the connection? Like
it could.
Like what's the... Basically, I wonder if there's because right now what exists is totally non-invasive. So you put on a helmet.
Yeah. Then
for the real things, they shave your head and they put gel on.
Exactly.
Right?
Yeah.
But that's not a consumer. That's not consumer friendly. And then they actually drill a hole in your skull and put electrodes in. That's the Neuralink approach. I wonder if there's a tattoo or other input-output port approach that's not. You don't have to drill through the skull.
That's a very good point. I don't know. But these are great questions. I mean, this is what if question. Yeah. It definitely would be important to. By the way, recently there was a paper in Science, I think a couple of weeks ago, 3 weeks ago, co-authored by Mark Brangersma from Stanford, that they use a very interesting material that made the skin of the mouse transparent for a short period of time, so they could actually send the light into the system. It's quite fascinating. In other words, temporarily you can make some opaque material transparent. Could that work, for example, in the skull? I don't know, but that's an interesting question.
When you were teaching this course together, what was the most surprising fact that the neuroscientists didn't know? Well,
it's interesting because the students we have were actually come from different departments, as you can imagine. And the surprising point was that the students from neuroscience actually were learning some aspects of electromagnetics. And the students from engineering part, they learned some aspects of neuroscience. So it was interesting. And by the way, I'm always in favor of interdisciplinary work, and I've done that in my career, is that it's always fascinating to basically go across the field. Because you will learn something new, and that would actually, with that, first of all, it makes your research very interesting, more invigorating, but also you notice that there's an interesting connection that otherwise you would not have known if you hadn't gone to the other field. And that connection usually leads to interesting discoveries and invention, because usually those invention happens at the boundaries, more in the fields.
You mentioned that you knew you would go back to academia after doing, so I think when your heart, you wanted to be a researcher, scientist, professor, and so on, maybe a educator and so on. Where did that, was there a culture of that when you were growing up in Tehran, like when you were doing your bachelor's, or like kind of where did that come from?
Actually, somewhat similar. A couple of months ago, I had an interview with ACS Photonics, Roman Kidan, and actually that interview came out 2 days ago.
We just saw that last, exactly. I read it last night.
Exactly. So I told him that as well. So as I was growing up in Iran, generally to be engineer and scientist was very well regarded. But when I was in high school at that time, I didn't know. I know I want to become scientist, but scientist in what field? So one day, one of my older brothers was working in this battery-operated transistor radio. And this is probably was my 1960s, you know. So I was just watching over his shoulder, and I was puzzled, how is it this little gadget is not connected to anything, and still sound is coming out of it. So I asked him, I said, how does this work? And I had no idea in those days, the working of this gadget. He said, well, there is a signal, there's a wave coming from radio station to here, and this being captured by the antenna of this gadget and goes into that, and it's being processed, and eventually that signal pushes some loudspeaker and the acoustic signal come out. I became fascinated instantly by this. What kind of wave is that? How come we don't see it? All of these questions. So I asked him, if I want to study this, what should I do after high school? I was in high school at that. He said, well, you should go to electrical engineering. That was the first time, by the way, I actually heard that there is a field called electrical engineering. Because in those days, in Iran, when you hear the word engineering, and somebody is engineer, the first thing came to your mind at that time was civil engineering.
Bridges.
And it was bridges, buildings, and so on. Electrical engineering was very, unusual. So he said, yeah, there's a field called electrical engineering. Hold on to that. Then, again, in those days in Iran, if you wanted to become scientist, you would go to engineering school. Now, that's interesting. You would go to engineering school to become scientist. You would not go to, for example, Department of Physics. Because in those days, there was no PhD program in Iran for science and engineering. So if you had gone to Department of Physics, after that you become a teacher in high school for physics. But if you wanted to become scientist, you would go to engineering school in those days, because there you actually also learn the science of engineering. So it was more like electrical science. So I went to the EE department of University of Tehran, and that was one of the toughest departments to get into. And I learned some of the fundamentals of electrical science there, and later on at Caltech. So I'm very much indebted to these two institutions, Caltech and University of Tehran. In University of Tehran, we studied the fundamental mathematics and so on. At Caltech, we studied obviously more advanced topic, but perhaps more importantly, at Caltech, I learned how to be a scientist. In other words, how to be courageous to go into a new field. Don't be afraid to go into a new field. In fact, at Caltech, effectively, there's no boundaries among the departments. You can go and take any course you want. You can take any field you want. You are not afraid to go into a different field. And that philosophy, by the way, really taught me a lot. And I'm very much indebted to what I learned at Caltech. Last year, I was selected as one of the Caltech Distinguished Alumni. And I told them, by the way, they had an interview similar to this through the Zoom. So I said, I'm very much indebted to Caltech because the environment was amazing. Is that you can do anything. In other words, yes, you are in electrical engineering, but you can do physics. That's what I did. And so that's coming back to your yes. From that time, I wanted to be a scientist. And then when I came to the United States and became familiar with the way US universities operate, so in order to become scientist, I said I have to be in an academic environment because I can have a freedom to choose my own directions, my own ideas. And I went to industry for, so sometimes, of course, when you're looking for academic position, you may not find the position you want. So I said I use that one to go into industry and to learn something there. And that was actually also useful, as I mentioned. And that experience helped me a lot. And then when I came to the University of Pennsylvania in 1987, I was so excited to build my own group. And I've kept that excitement in the past 37 years. And it's just, as I mentioned, I teach this graduate level course in electromagnetics and optics. And I tell the students, this is a fascinating topic. I've been working on it for 40 years. And every day I'm more excited about it because there's so many things EM waves and light can do. I think that sense of excitement, and one of the reasons, by the way, that I keep this excitement is because you can do new things. And you can ask new questions, and that's important. And the connection among fields, and that brings me to optical metatronics.
Okay.
Misha's finally getting.
Yeah, I'm trying to merge the two worlds of electronics and optics. But also maybe before asking this question,
Sure. Okay, good.
how will you make it at the end? You touched the base on optical computing and how it could be useful for AI. My question is about, so now electronics is so advanced on the side of the computing especially. And optics is at the very early stage.
Not necessarily early, but yes, okay,
quite early comparing to what,
yes, sure.
like NVIDIA chips, like the GPUs, and like kind of crazy neural nets we can build and implement. So how do you see, what would be the moment, would optics be able to catch up with electronics, or what's now like the main bottleneck for electronics, which will, would limit its applications in computing?
Right. Excellent question. Let me first say just from the start that even though I like optical computing, but I'm also very much in favor of electronics. Don't get me wrong. Both of them are needed. No question about it. Electronics and photonics each have their own set of advantages and also constraints. No question about it. For example, let's pick one thing. For example, if you look at digital electronics, in other words, digital processing, digital logic, clearly CMOS technology is doing amazing job. And we are doing great. In fact, in the year 2010, David Miller, my good friend from Stanford University, wrote a very interesting paper in Nature Photonics in 2010, discussing how hard it is to have an optical logic, meaning optical transistor, given the basic functional requirement of light compared to electronics. In other words, the electronic transistor is far better than optical transistor for a very interesting set of reasons that he clearly mentions in his paper. And this is very, very important point he's making. In other words, if in his opinion, and I agree with that, and my opinion as well, is that if we want to do digital logic, digital electronics, we stay with electronics. Electronic does that.
Is it because electrons interact with each other?
It's because, well, I mean, one thing is as according to David in his article, and I highly recommend that you look at his article, 2010, is that, first of all, the critical biasing that you can do in electronics, in optics doesn't exist in that sense. You can bias the transistor far easily in this one. Another thing is that transistor, the nonlinearity there is wonderful. Optics nonlinearity is very weak. And that's one of the bottlenecks, by the way. And we can discuss that in more detail if you're interested. But I agree with David that the digital logic is doing far better job. So from the point of view of digital system, electronics is doing great job. In my opinion, the optics, it better stay away from digital aspect. However, by the way, there are other aspects also. Nonlinearity is another one that the electronic is doing great. In electronic, diode is an amazing element. We don't have that easy one-way system in optics. Yes, you can do non-reciprocal system, but that's not as efficient as regular diode that you get it from electronics too. These are very important aspects. So electronics is doing great there. Optics. So in optics, there are advantages also in optics compared to electronics. For example, optics can have great bandwidth. So as a result, you can have more information there. Another aspect of optics is spatial modes. You can have a lot of modes within a system. Whether this mode would be inside the waveguides, whether this mode would be just propagation. Look at the lens. I mean, a lens can do Fourier transforming in one shot. That's amazing. That's just because all the spatial mode that you have, the wave can propagate different angles, different directions there. Another thing, of course, is parallelism. A parallelism in optics is amazing. Electronic does not have as much parallelism as optics has. That's very important. For multi-frequency parallelism, you can have in a single region, you can have different colors go through this and would do different processing there in optics. So I mentioned about the digital. So naturally, one would think that when we want to do optical computing, we better stay with analog. And that's quite fascinating because analog system can do its own thing. However, analog system has its own constraints. So we have to be realistic. Noise, clearly. Digital system, because of the digital system, you can actually get rid of that variation of the noise. And that's one of the beautiful aspects of Boolean algebra in digital system. In optics, noise obviously is there and inherently. So the natural question to ask is that, yes, with all the advantages that I mentioned for optics, we need to choose an application area that would be applicable to that the noise doesn't affect that. Let me give you an interesting example. Our eyes can do amazing things, by the way. If you look at it, this is analog system. In the presence of noise, our eyes work beautifully. So optics can do a lot of interesting things.
Very energy efficient.
Very energy efficient. Would you say that the optical components of the eyes are doing that, or is it then after it's already converted to an electrical signal?
A good question. No, I would say I meant mostly from the point of view of lensing system that we have. Yes, eventually when optics gets to your photoreceptors, and at that point it turns into electrochemical signal that gets into your brain. That, of course, part of this is electronic, yes. But before it gets there, and the image that's formed on your retina, that's purely going through the optics in the materials and lens that you do that. And there's a noise there. No question about it. the molecules of visual pigments in our photoreceptors will pick up the signal, yes, in the presence of the noise, still it works. So what I'm saying is, yes, the analog system could be noisy, but that should not scare us, because there are many applications that the presence of noise may not be, that crucial. If the application requires the tremendous precision, we better stay with the electronics and digital, yes. But if the application is something that it's okay to have some noise, then the optics can do a great job. Imaging, one aspect of it. Sensing, another application of that. Vector matrix multiplication.
Surprisingly.
Yeah, exactly, yes. Can do that. Inversion of a matrix, the one that we have shown, can do that. And maybe some more, coming along. So we have to be judicious in choosing what aspects of light can help us in computing, what aspects of light electronic can help us. And we shouldn't be prejudiced one with respect to the other. Whichever works, that will do. And in fact, in my opinion, it's a hybrid system. Eventually, it's a hybrid system. Electronic is fantastic in storage. Optics storage is very hard. In that case, we have to also take into account the fact that yes, you do as much as possible, you do with optics to do the processing and computation, and at the end, you may store it electronically, and so on there. Optics can do another interesting point, and that is very low, very small latency. And that's not necessarily just the speed of light. Yes, the speed of light is very good. We all like that. But one can argue, in fact, Peter McMahon from Cornell University has a very interesting review article. It says, if I even take some wires and I connect from this point to that point, that can also go with almost speed of light. Even coaxial cable can go with the speed of light. So yes, the speed of light is important, but that's not the reason that the light optics is good. It's a latency issue that would be better, because every time in electronic we do certain processing, analog to digital conversion, or the vice versa, digital to analog conversion, all of that takes energy and takes time. And that adds to latency. If we can do as much as possible with the light, that brings down the latency and the throughput becomes much better in that regard. So that knowledge is very important to consider that. Coming back to your question, is that with regard to the why light, I think can play a very important role in AI, precisely with this application in mind. In fact, in AI, as you all know, particularly in the neural network, remember, of course, Mike, particularly with regard to the point that you mentioned, one of the aspects of those layers of neural network is vector matrix multiplication. And vector matrix multiplication is a very good point for optics because it does it naturally. So any scattering is a vector matrix multiplication. Any scattering. That's how I got interested in that from metamaterial point of view. After all, metamaterial, you will design them to have interesting properties like index near zero and so on. Then we said, why not do it in such a way that you can have solving an equation? After all, if that is the goal, let's actually design something that you send a wave through this would do solving equations. And that's how, my thinking worked that way. Another thing, by the way, is, as I mentioned, nonlinearity. Nonlinearity in electronic, of course, is prominent. As we talk about the transistor, diode, these guys are wonderful nonlinear element. Optics nonlinearity is weak. So if we want to choose an area of computations, we have to be aware of these constraints and advantages of optics versus electronics. And again, both can be very useful in their own domain. Another thing, by the way, is also what happens if you have a signal in optics and you would like to actually distribute that to several points. Optics can do much better job than electronics. With wiring, it might be harder to get it, whereas optics is naturally. Likewise, you can actually concentrate the signal at the point, whereas in electronics that would be harder. So there are several aspects that optics can do better than electronics, but there are many aspects also that the electronics can do better than optics. So that's quite important to consider that. Coming back to the AI, I think yes, vector matrix multiplication is naturally to be there. But of course, also in neural network, you need nonlinearity. So again, you see some of the things that optics can do, but then nonlinearity, electronic can do better. If we can improve, and that's one of the interesting direction that one can take, is that how to enhance nonlinearity in optics. a lot of work going on in that regard, particularly using quantum engineering. People have shown, I am sure you're very aware of it, I've shown few photons nonlinearity. That's fascinating work. An interesting point is that if those type of few photons or single photon nonlinearity can be brought into this AI region, that would be quite fascinating. So if you do vector matrix multiplication, as you know, in the case of neural network, you need to turn that into a signal, either using sigma function or using ReLU function. Can that be done, for example, optically? Right now, that requires some energy. If one can do that with a lower energy, that would be a big step, in my opinion, forward.
Together with Michael, brainstorm on like the optical tasks which could be implemented. One of the use cases, I think Michael had worked on it for a while. It's like put it in the blockchain. So we brainstorm what kind of problem nowadays can be solved by optics, or maybe like a set of problem or problem which could be stand out comparing to existing electronic solutions. Is there such a problem which you can solve optically faster than having all these GPUs and advanced electronics right now?
I mentioned few of them. Imaging clearly would be a good thing to have, sensing, optics, vector matrix multiplication, but also I say inversion of a matrix. And that's one of the reasons, by the way, we decided to do solving equations. The way our thought process worked was that we said, okay, can we design a metamaterial that would do mathematical operations? And that was our work in 2014. We came out. By the way, again, from the point of view of just thought process, because one of the reasons behind this podcast is how did we think about that? The reason I thought about it that way is really goes back to 2005 when we introduced the concept of optical metatronics. One of the reasons I introduced that at that time was to actually think about photonic processor. Because in electronics, we have the circuit elements and you put them together and you have electronic processor. So I said, one way to think about that is that if we can have nanostructures that behave as those circuit elements, can I put them together in the nanoscale and have photonic processor? That was the thought process. And then eventually we did it in a sense of coming from 2005 to 2014, 2019, and now. So one reason is that after we did the work on how to design a metamaterial or metasurface that can do mathematical operations, and at that time, the low-hanging fruit application we were thinking about is in image, edge detection in image. And that's clearly one application that optics can do far better than electronics. Because if you want to do edge detection in a regular electronic system, you have to raster scan the image. You have to compare every two pixels next to each other to find out the difference and find out what is the edge of the image. But in optics, you can do it all in parallel, an analog system, and noise is okay. There's nothing wrong with the noise there. But then a follow-up thought with that, okay, now that we can do mathematical operations with metamaterial and light, can we solve an equation? Because after all, an equation, by the way, when I say equation, differential, integral, or interdifferential equation, I'm not talking about algebraic equation. That's some of the things we are working on that right now. But we're talking about the another equation that has operator in it. So that's how we came to that point. In order to do that, we have to have a feedback system, all the details. And that allowed us to actually invert a matrix. Now, why inversion of a matrix is useful? That's a fair question to ask. And it's useful in the following way. And right now, actually, we have a paper that's just about to be accepted in Nature Communication coming out, and in which we showed, using electronic elements, by the way, but the concept, we showed that if you have a 5x5 matrix, and you would be allowed to actually change the element of this matrix at will. Can you invert the matrix? Okay. And we showed we can. But based on that inversion, can you go back and change the matrix again and invert it again? Change the matrix again and invert it again. So based on the knowledge that you gain, you go and change it, invert it, and then you go and change it, invert it, and go change it. Why we were interested in that? Because that's the basis behind optimization. So in other words, can we do optimization using waves? That is one of our goals. And in that, we need to invert the matrix. After all, you're all familiar with inverse design. So the way that actually optimization of inverse design mathematically works is that you start with some uniform permittivity and you find the outside and you compare it with your objective function. And based on that, you go basically gradient descent and you try to do this. So every time you do that, you have to actually solve the problem, scattering problem. And the scattering problem is integral equation problem. In order to solve that integral equation, in a way, you have to invert the matrix. We said, can we actually do that naturally with this structure? Obviously, that means that that you have to have a system that you would change that Swiss cheese. And that's something in our ongoing work. But while we are working on that, we wanted to show that if we can actually have the capability of reconfigurability and programmability, what good do we have? So we didn't want to wait until this material gets to the point that we can change it. While we are doing that, let's just show the advantage of that. That's what we build actually in my lab, a 5x5 electronic element. These are low frequency 45 megahertz electronic element, just to show the proof of concept experimentally. And we showed that yes, you can actually invert the matrix and you can actually change the matrix and invert it again. And this process actually can lead to what you want. That's what we looked at, 2 toy problems in this paper. It's on archive, you can see it, but it's going to come out very soon in Nature Communications. And so we showed that if we have 5 scatterers, that their locations are known, but their epsilon is not known, and you would like to choose that epsilon such that it will give you certain scattered value at 4 points, for example. What should those epsilons be? That's an inverse scattering problem. That's an inverse design problem. This gadget actually told us that. It actually go through this process to do that. So I'm very optimistic and very excited about that, because if in the future we can do that with actual material, this is electronic, but we can do that in actual material, that would be quite fascinating to see we can do that.
So how difficult is to scale up this, you said 5x5 matrix? Can you do 500 by 500 or even larger?
Excellent question, and that's a very fair question. Obviously, that's a very challenging one. Right now, we have shown it 5x5, both in the microwave as well as actually in the optical. Well, we did it 5x5 in microwave. In the optics, we did it 3x3. Recently, we had it the vector matrix multiplication on the silicon photonic platform. So very recently, we brought that concept into silicon photonics. And the reason we did that was because we wanted to actually do it the possibility of mass production. Because one thing is to have a nano fabrication technique. That's one of our goals, that at some point this concept comes to silicon photonics that we can do that. There we did it 3x2, 2x2, yes. It is fair question to see if we can do it larger. And in fact, we started working on it. We said, okay, exactly the question you had is that, okay, can we do it 30 by 30? Can we do it 100 by 100? The way we try to address that problem, we said, okay, let's go step by step. Rather than suddenly jump to 100 by 100 with a completely a general kernel, we said, okay, why don't we actually restrict our range of possible kernels that we have for a specific application? For example, if you want to do imaging, okay, in imaging, the kernel has a specific class of kernels, and that's known as banded matrix kernel, because it's convolution. So imaging does convolution, okay? And the advantage of convolution is if I do it here, I can do it here, I can do it here, I can do it here. So what we decided to do, rather than having an inverse design for something that is 100 by 100, we said, why don't we actually have a unit cell of that? Kind of like a stem cell idea. If I can have a unit cell of that, such that I can put it next to each other, all the same, but it would do the mathematical operation of a specific convolution we have in mind, can we do that? Because after all, that would be one design, and then you can repeat it next to each other all the way there. So we decided to do that. We designed the system for the wavelet transform. And we sent it to the foundry in almost 4 months ago, June 14. So we're waiting for the chip to come back. We'll see. That would allow us to have more. This one that we designed is for 32. 32. There's no magic number about 32. It's just that was the room we had on the chip. In principle, that go to 100. But again, that's for the specific class of kernels that we have banded matrix there. So yes, if you want to go to the much larger scheme, in principle that would be possible, but for a specific class of kernels, at least so far. This is an ongoing work that we do to see how we can expand that to further. There are also constraints with regard to the noise as well. That's a valid point, because if you have a very, very large matrix and you have a signal coming from one port of it, you want to know whether the signal that you get at the other port is above the noise level that your detector can detect.
Yeah, I see. With electronics, that's what like photonics electronics also like comparison. Like electronics, you can do like density of billions of chips on transistors on an inch, and then with photonics, I feel like the footprint is one of the bottlenecks, but hopefully with
exactly.
fabrication techniques.
But again, electronics certainly is ahead in that regard, no question about it. The optics, it's not there yet at this point. But again, it depends what we want to do. For example, one possibility here, by the way, the one we have just designed back in June, we sent it, it's on silicon photonics. But this doesn't have to be on silicon photonics. This could be just a metal surface. If you have a metal surface in this direction, you have no limitation, so to speak. So if you can design a single unit such that when you put it next to each other, you would actually do the kernel you want, that's possible. So in that case, in principle, you have no limitation in this regard. Now, in this case that Michael was showing, I assume that you have a wave going in this
it's all in plane.
It's all in plane. And of course, that has its own constraint. But if you for a moment put the silicon photonic aside and we design a metal surface that the light comes normal to that, then in this direction, you don't have that constraint. So that's something we are looking into that as well.
One thing I want to mention is that actually a single transistor is very small, but if you actually want to do multiplies and accumulates, which is what you have to do for a matrix vector, it's not that a single transistor is doing a MAC, right? So you're performing a lot of computation in the optical component, so it's not like a one-to-one
exactly
in terms of the size of the optical component and the transistor.
That's
so
a very good point.
You have to think about how many multiply and accumulates you can perform.
But in terms of like, let's say if you take GPU, how big of a matrix can you put in there? It just depends its memory.
This is not, even though I worked sort of tangentially to this field for a couple of years on the optical computing projects, it is not my area of expertise, but GPUs typically, it's not that they perform the entire, so if you have a 500 by 500 matrix vector multiplication, it's not being done in one shot. Right, so that's one. What the GPU is good at breaking it up into pieces and then doing it over
like elementary logic.
Yeah, multiple clock cycles, right? So you have to. It's kind of a different calculation, but in terms of like space efficiency, it's not a given that because the optical component is larger that it's actually less space efficient. You have to look at the entire stack up of like exactly, and just also with electronics, you have heat dissipation. So like you can only make the chip so big and so on. There's like multiple, it's a super applied, very big space which you optimize in. But I think, the traditional thinking is that optical components are really big and you have to find components and so on to get smaller, but that might not be true. I don't know.
No, that's a very good point, Mike, you mentioned, and thank you for bringing that up, because that actually is another point I wanted to mention and I forgot with regard to possible advantage of optics versus electronics and so on. First of all, one aspect is that in optics, when you want to do vector matrix multiplication, the wave propagates to your system and you get over here. So you achieve the output vector with a very small amount of energy loss, if you think about it. Strictly speaking, you have some energy loss because of scattering in materials. Whenever you have materials, you have dispersion. Dispersion means loss. But it's much less than if one wants to do it with electronics. That's one fact. But another thing, by the way, is that in electronics, in order to do this operation or flops that you have, you follow the clock rates. So if you want to multiply a vector by a matrix, every clock of the system would do part of this. This one, and then you have to add them up. So there's a lot of operations you need to do in order to achieve that vector matrix multiplication. Whereas light is doing it in one shot. There's no clock rate there. It's just light coming from here to there, and you have the vector at the output of that. Now, saving that vector and so on, yes, you have to turn it into electronic, but the operation of vector matrix multiplication can be done naturally through the scattering. If one wants to do it with transistor and so on and so forth, that obviously it's done very nicely, but it's done based on this optical rates that you put there, and every operation has to come, and every operation has its own energy cost that you want to do it. So that's something to take into account. What Mike said is also quite important, is that it is not fair to compare a unit element in electronics with a unit element in optics. Because one can say that, okay, in optics has a wavelength, I don't know, 600 nanometer, or if telecommunication wavelength 1.5 micron, so we can do anything in that small domain. But the important thing is that what operation can be done with the collection of that. Again, I'd like to mention the example of our lens of our eyes. It's a sizable amount, but it does a lot of those imaging of our retinas. If we wanted to do that electronically, at every point the transistor has to pick up photo detector and do it, But then light is doing it right there and brings it. Or if you want to do, for example, Fourier transforming or other transform. By the way, that was one of our motivation when in 2014 we introduced the idea of metamaterial that can do mathematical operation. In fact, our logic at that time was this one. A regular lens would do Fourier transform for you. But why should we stick only with Fourier transform? Why not any other operator? Can we actually have our own quote-unquote lens that would do different operations, differentiation, integration, you name it, convolution. Now, for example, we designed something for the wavelet transform. We see how that would work when the chip comes back. Or other operation, other linear operators. Edge detection, we did it with the second order derivative.
When I originally got into looking at all the optical computing, I read a lot of old papers. Optical computing, occasionally people try it, like at every time, every 20 years or something, there's better. So now it's silicon photonics, used to be something else. But I think the lab, I was looking like, when was it really successful? And one of the things that I found is that in the 70s, for like missile guidance, they were using some optical system, but it was fully analog. So basically, you would have image detection, because it's trying to, I think it's probably in the infrared, hitting a hot target. Right? And just searching for edge detection or whatever, that type of thing with the Fourier transform directly in the head of the missile. So you have some lenses, they're doing the Fourier transform, and it was somehow turned into the guidance. There also used to be another thing, I don't know if you've ever seen this video, but they used to train pigeons to do this.
Yes.
So they have a TV screen inside the missile, and the pigeon is there's like a target on the TV screen. The pigeon pecks at the target.
I see.
That
I have not seen.
That's like the neural network part of it.
I see.
Yeah. So the pigeon pecks at the target, and that turns if the target goes off center, pigeon pecks at it, and it turns the.
I see.
So they were trying everything.
Very interesting.
But I think there were some commercial systems that were all optical to do. Maybe at the end there was a detector, and then based on something they would turn the missile.
Sure.
I think an interesting question is whether, now there are some really advanced optics in transceivers. That's probably where the best chips are, right? They're trying to pack as much as they can into one fiber and so on. So I think one interesting question is, if you start with an off-the-shelf transceiver, but you connect it to some kind of system that that's built for computing, what can be built out of that? Because in some ways, that's like the billions of dollars that have been put into transceivers. Now those are, they're dirt cheap basically. So the question is there a way to get computation out of those?
Absolutely.
That's kind of one
and
of
it's fast, right?
Yeah.
Well, the transceivers are extremely fast. They're built,
exactly.
in huge volume and everything.
Sure.
It's kind of like the thing that really works right now in optics, right? So anything you can do that's based on a transceiver or on a commercial type transceiver would be much more scalable. So that's one thing that I thought about. I could never come up with anything, but
sure. But that's the point is well taken. Absolutely. If one can make, for example, design a metasurface that get the image and connects it to transceiver, fantastic.
Something like that.
That actually is consistent with what I mentioned a few minutes ago, that there are certain application area that the analog optical system can help with a very specific task. That's another thing, by the way. Sometimes there is this confusion. They say, okay, well, can optical computing be all-purpose computers? Well, we do have all-purpose computer that's working very nicely. But optical computing could be very good for task-specific. That's the key, at least to start with. Now, who knows what's going to happen in the future. But if we actually go based on task-specific case, I think that's a good direction to take this field. Yes, programmability is very useful. As I mentioned, one application of programmability is optimization. If we can do that with light as much as possible without at least or little amount of electronics, that would be great. And because every time there is a conversion or connection between optics and electronics, there's an energy cost and there's a latency. So we have to be aware.
This is one of the things I was going to ask about is because of all these systems, if you look at a lot of the published work, or even there's been companies that have tried kind of like, there's been a wave of silicon photonics computing companies that are trying to make this work. You always get stuck or that's one of the sticking points. There's the noise, there's a lot of things, but one of the sticking points is the ADC and DAC conversion.
Sure.
I wonder if you've thought about either analog systems that are optical plus analog electronics, so you never have to go digital.
Sure.
Or all optical systems that are doing something akin to like image processing and then responding to the image, or something where you can stay in the optical domain completely.
Yeah. Actually, the latter one, I think that's the one that I've been interested in. In other words, to stay in optics analog as much as possible. If there is a possibility to actually turn the analog into analog electronic, that would be better, rather than going through the digital aspect, because that costs energy and time as far as latency is concerned. So that's one of the reasons, by the way, that we decided, in fact, that's one of the reasons that we wanted to see whether we can actually solve equation using that, rather than have parts of the kernel in optics and then do electronics. So can we actually have a system that does everything and find the solution? It was through that, thought process that let's try to avoid to go into digital system. Let's try to avoid to go into electronic as much as possible. But again, I always mention that electronics is extremely important. We need them. We need to actually combine them, and eventually the hybrid system is the one that obviously would work. After all, more from physics and philosophy point of view, in nature we have electrons and photons. We should take advantage of both of them. And each one of them had their own advantages. But yes, but one thing we haven't talked that much, and I think is also very important, is nonlinearity. I think it's very important. This is something that, in my opinion, is less paid attention to. Nonlinearity is very important in electronics, and it's there. But optics nonlinearity is weak. Microwave nonlinearity is actually strong. There are a lot of microwave elements that are nonlinear, simply because the frequency is lower, simply because electron takes time to move from here to there, so you can actually use nonlinearity. But it's quite fascinating to see how quantum optics, quantum engineering is going to help us in enhancing the nonlinearity. Just imagine in the future that such a quantum system that can enhance nonlinearity as much as possible, as much as the physics of light-matter interaction allows, to actually make the nonlinear system there. Imagine that in the neural network, if you do vector matrix multiplication by light, and then at that point you would like to do the nonlinear flattening of that, basically, that also can be done with light. That would be quite fascinating, provided that the energy cost is low. That's one of the things, by the way. If you want to do nonlinearity in optics, you have to have minimum amount of energy to trigger that nonlinearity. And if you can bring the trigger point lower.
What do you think are currently the most promising systems in which to achieve this nonlinearity? So you were mentioning quantum engineering.
Exactly. There are quantum bandgap engineering that some groups have done. They have done also with a single photon or few photons nonlinearity. That's another fascinating point that, it would be interesting to see what would happen if all of this optical system that we are talking about really go to the very low photon numbers. Of course, one has to be careful with regard, to all the noises again and so on. But in reverse, in other words, can we apply the technology that has few photon nonlinearity to many, many more photons that the regular optical system can use? And you don't need to use very low temperature system and so on to get the noise. I'm optimistic, by the way. I think quantum engineering can have a great contribution there with regard to enhancing nonlinearity. And you mentioned, by the way, in the break that neural system have huge nonlinearity.
Neuromorphic computing?
There's huge nonlinearity. But of course, physics of light gives us very weak nonlinearity, but there might be an interesting techniques, as many groups have been looking at, to enhance the nonlinearity.
Yeah, because most of the approaches were rather coming from field concentration, using these nanoparticles, nanoresonators.
But those have the losses.
Yes,
that's the thing. Those have their own constraint. They have losses in the. And then again, from nanofabrication point of view, combination of metal and dielectric would be hard to have. That's true. But if one can actually do some of this bandgap engineering, some groups have done that to see how they can enhance the nonlinearity in semiconductors. But also in quantum optics, several groups have looked at single photon nonlinearity. If that can be expanded to higher number of photons, and particularly in the system that can be implemented in a more practical scenarios, that could be quite a fascinating possibility.
And for nonlinearity, is there, let's say, a range where it's like good enough, or we need to go to that quantum regime where you deal either with single photons or the...
But that's the thing. It's
resonators.
ideally you would like to have it such that with the low threshold level of the power, you actually trigger nonlinearity. And that comes, by the way, there are different work going on. EMZ is one of them, by the way.
Maybe an interesting question is just where does nonlinearity come from at all? In
Oh,
optics?
sure.
That's
That's right. I mean, of course, there's different aspects of that nonlinearity. Essentially come with the fact that in the regular system that you have, the harmonic oscillator there, you want to actually make that anharmonic in a sense. And that's what, in order to do that, you need power to bring it to the point that then it doesn't follow that aspect of that. So that from the material perspective, that's the case. And that's a challenging one. And there's a lot of work have been going on in that regard. On the other extreme, if you just go to the single photon aspect, then you say, okay, if I have one photon that excites the electron, the next photon doesn't have electron to excite. So there's a difference between one photon going through and two photons going through. But that will be at the very fundamental level of the single photon. Can that effectively come to a point that you have enough number of photons that could be doable within things remains to be seen. And by the way, I mean, if you look at, for example, nonlinearity in microwave, that's of course readily available. And one reason for that is because the frequency is much lower than optics. As a result, electrons can have more swing variation, and then you can actually affect that electrons. But if the electron goes so fast at the optical frequency, there's not enough time to basically, that's another way of looking at that aspect to affect that nonlinearity. But yes, I think that's one of the very interesting direction in my personal view. It would be fascinating for optics to do. Sometimes in the class I teach, I tell the students, imagine think about your auditory system. Our auditory system is an amazing nonlinearity. You can hear a mosquito and you can hear a cannon. That huge range. It's amazing. Of course, it's because you have gain control and so on in the auditory system. And many aspects of biological system has a lot of nonlinearity. You mentioned about neural system. Wouldn't it be nice if actually we had huge nonlinearity in optics? I mean, it would have been a different world, by the way. I mean, really. Of course, the laws of physics prevent us to a certain extent, but it's interesting that maybe in the quantum level would be something that can be done.
It's like so many different systems you can do computing with.
Yeah, literally. By the way, on a different, somewhat related, metamaterial, for example, a lot of interesting features in metamaterial, but people in acoustic also apply some of those ideas in acoustic metamaterial. And because in acoustic, nonlinearity is much higher than things, they can actually see interesting points. So yes, that's a different physics, obviously. That's different wave phenomena than optics. Yeah, but sometimes it's interesting to see how the other wave phenomena can deal with nonlinearity and somehow we can get inspiration from it.
So one question that we'd like to ask our guests is, if you had infinite resources, what would you work on? And it seems like it could be nonlinearities.
Well, that's one. By the way, there's so many interesting directions to go. The problem is resources and time.
Let's say time is also
exactly.
And students.
We are always
More
limited.
students.
You know, you guys are young. So you have plenty of time. Yes, I mean, I would say, by the way, as a more general aspect, of course, nonlinearity is a very specific direction, but a more general aspect, we touched upon that earlier in our discussion, how to actually use optics in artificial intelligence. How can that really revolutionize that field? We talked about optical computing a lot. I think that can play a very important role there, given even its limitation of optical computing that we listed and we discussed. Because one of the interesting points is that I remember back in 1980s, the issue of neural network at that time came, and people like Dimitri Soltis and Nabil Farhat, these guys were pioneers, by the way, in optical implementation of neural network back in 1980s. I remember I met Well, when I was graduate student at Caltech, Dimitri Saltis became assistant professor there. And so he was actually in my PhD dissertation defense. Dimitri Saltis later became a prominent faculty at Caltech and later on moved to EPFL, became the Dean of Engineering there. So in 1980s, Nabil Farhat, who was a professor at University of Pennsylvania, and later on I became his colleague when I went the assistant professor, was actually on sabbatical at Caltech. And that's how I met him for the first time. And he, Nabil, and Dimitri together actually did the first, to the best of my knowledge, was the first optical implementation of neural network. And in those days, they did it with the optical modulators and so on, and with the optical fibers and so on. So they showed that indeed that would be possible. So as it happens in different fields, sometimes the things come and revisit maybe a couple of decades later. So the reason now we have a lot of interest in AI, neural network, because the computing power have increased so much, both from the hardware point of view and from software point of view and from data storage point of view have come to this point. But the future could be quite fascinating to see how optics, given within its own limitation, can actually contribute a lot to the computing. And when I say computing, I mean in a very general term. I don't mean just vector matrix multiplication, although that could be one, but other things that in the future as that. Yes, I think that if we have infinite time and infinite resources, I think that would be a quite fascinating direction to take that. Within that, of course, nonlinearity is one of them that I just mentioned there. I would say, by the way, another thing is that the whole concept of nonlinear dynamics, it's quite fascinating, and to see optics, of course, optics has already played some role there. But again, one of the interesting points, and also I mentioned this to Roman Kidan in the interview he had with me, is that the concept of emergence. When you have many, many things put together, the dynamics of that would be different than individual elements. Optics can do that too. I pose it as a question. How the combination of optical signal and also electronic signal together can actually come out with an interesting phenomena that we don't see individually, but we see it as an emergent process that will come over here. So the whole area of nonlinear dynamics, chaos, and so on is a quite fascinating direction. And I'm curious, I haven't done anything in that field, but I'm curious to see how these things would be. Just again, a curiosity-driven question. Can optics play a role there? And to have fascinating possibilities there. And there are many more, by the way. Obviously, there are always more questions than answers, and that's a good thing about science. That every development that we do leads to finding a solution to some question, but creating more questions, and that's good.
A lot of in our audience, we have young researchers, young scholars. Anything would you give an advice for them when they start a new career?
Yeah, I'd be happy to do that, but I think I haven't answered your question about optical metatronics.
Metatronics, all right.
Yes.
Yeah, I mean, I know you like that subject, but the things came out and so on.
This, yes.
Yeah, I mean, just to finish the thought.
Sure.
Yes, absolutely.
See, my interest and expertise and training have been both in physics and electrical engineering over the years, both as a student and also later as a scientist. So I'm always fascinated by the connection among the fields. And so I remember many years ago, as a young researcher, I was always puzzled by this question that why is it that in electronics, remember I come from microwave, in electronics we have lump circuit elements. I used it all the time. But in photonics, we didn't have at that time. After all, these two fields follow Maxwell's equation. If you look at Kirchhoff's voltage law, that's an approximation to Faraday's law. And if you look at Kirchhoff's current law, that's an approximation to continuity equation. So how come these fields, even though physics of the field is the same, but historically they actually evolved in a very different direction? One direction is for lump circuit element, very modularized version, whereas optics was more like a wave. This question was puzzling me for several years. Until when I got into, as I mentioned, in 1980s and later 90s, I got interested in interaction of waves with materials, chiral media, all of those things we discussed. I said, is there any way that we can do that? Of course, the reason is in electronics, the frequency is very low. Every element is much smaller than the wavelength. All of those things there. But there was another bottleneck, by the way. The bottleneck was not just the size, because with nanofabrication, okay, I can make a little inductor that is 100 nanometer. But that wasn't the bottleneck. That was one bottleneck, but that was not the only one. The other bottleneck is the physics of materials. Mm-hmm. One of the interesting points, by the way, that often we don't appreciate is in electronics, we have metals. It's amazing, by the way. We take it for granted, but think about it. Metal is an amazing thing because it would actually be a conduit for electrons to go from here to there. Mm-hmm. Recently, I was giving a talk in Metamaterials conference, actually last week, and I showed a picture of a circuit diagram of the black and white TV. I said, what is that? Those of you who are in electrical engineering may recognize this. If you look at it, there's all these wires going on. That's actually, in a sense, is electronic metamaterials because it actually manipulates where the electrons go. And by that manipulation, you do the functions. That's what metamaterial is all about in optics, that you want to have. That's what Swiss cheese is all about, that bring the light in the direction that would do solving equation or do the vector matrix multiplication. So I said, why is that we... So anyway, then in 2005, we came up with the idea that, okay, if you have nanostructure with the specific properties for epsilon, you can actually have an effective impedance that resembled the impedance of those lumped elements. That actually brought the fields of electronics and photonics together because it becomes the same set of alphabets. So the prescriptions that the people in electronics did design of this now can be actually transplanted into photonics, and that led to different things that we did with the nano antennas and so on and so forth, and then eventually to photonic processor. So that's how it came out again with this curiosity-driven question. What if we can modularize photonics? And can we modularize photonics? And in order to do that, we needed to have some equivalent circuit elements. And that's how the inspiration came from electronics and how we do that. That helped, by the way, to recognize the connection between this. And of course, by the way, just like analogy in everything, this analogy at some point stops. And each field has its own properties, obviously. And that helped us and eventually get to this point. But thank you for that question.
I think you have a special talent in bridging the two like different fields and finding like interesting what has been already found in one field, and then you can project it and maybe see it in another field.
Yeah, I love to actually go across the boundaries among fields in order to learn from that field. And when you learn from new fields, you can see the connection. After all, laws of nature. And the laws of nature works across this, but you start from some field and you're specialized in this and other people specialize in this. But the interesting connection among them, and when you see the connection, you will see the similarity, but also you see the differences, obviously. And we can learn from this connection. And sometimes, by the way, it's interesting, communicating with colleagues in different fields, often there is just the impedance matching. I remember sometime I was talking to a colleague from in optics. He says, this would be a critical coupling. I said, well, that's impedance matching.
Yes.
Yeah, that's right. We tell you, but it's good. Actually, it's good to have this discussion because then we can learn from each other and we can contribute to every field.
Did you at any point ask yourself, why hasn't this been done before when you were working on this? Like, why have other people not done this?
Yeah, exactly. And it's interesting because when you're talking about the optical metatronics.
Yes, the Metatronics.
Yeah, I was positive. Well, I mean, later on, I could figure out why that wasn't the case in the past. Because, of course, nanotechnology was not as advanced in the past. People thinking about having a particle that is a fraction of a wavelength of light. Of course, that was very hard to imagine. Of course, now it's very easily doable. And also material properties. So knowledge of those two eventually. And that's one of the things that I was very interested in the field of plasmonics. That's how I got actually in the field of plasmonics, through this optical metatronics, and to see how we can connect these two together. But I'm very excited about the connection among other fields. I mean, we talked about AI, so that's another interesting. There might be another interesting connections there. Nonlinear dynamics is another fancy. Recently, by the way, literally in the past few months, I became very interested in a very different field, and that is, I became interested in Kapitsa's inverted pendulum. Do you know what that is? Actually, I was giving a talk last week in Metamaterials. Well, you all know, obviously, the simple pendulum when you do it like this is stable. You know that if you actually bring the pendulum here, it's unstable, obviously. Back in early part of 20th century, in 1908, I think, there was recognition that if you actually have this pendulum over here and you move the base of it up and down very rapidly, but very small amount, this pendulum actually became stable back there. This was observed, but nobody knew. I could not actually mathematically evaluate why that is the case until Pierre Kapitsa in 1951 mathematically solved the problem very elegantly. I loved it, by the way. Again, recently I became aware of this topic. So I went back with one of my postdocs. We looked at this. He did a beautiful job, by the way, in actually mechanical structures to do that. And he showed very nicely that if you actually have a very small displacement of the base of this pendulum, but with a very rapid frequency, and there's a condition that that frequency should be greater than something, this pendulum becomes actually stable. Now, it's interesting, by the way, that that problem actually started a new field of vibrational mechanics. So there's a lot of interesting mechanical problems in which if you actually vibrate or modulate certain part of the mechanical system, the stability of the system will change. Even though the variation is very small, but it can actually affect the stability of the whole system. And in fact, there is a whole area that I'm reading about it. I call it vibrational resonance. So just out of curiosity, I said, can we bring this into electromagnetics? So we decided to actually look at this problem. Just a simple LC circuit. If you look at an LNC circuit, that's also an oscillator. The formulation is identical with the pendulum, mathematically. It's basically a second order differential equation with a periodic solution. How do we make LC unstable? By actually making the C negative. And there's a whole area in electronics known as non-Foster circuit elements, which C is negative. It has to have a gain medium. In other words, you have to have a transistor to do that. If you make C negative, of course, this system becomes unstable and you have an exponential increase of the current. So we ask ourselves, can we actually oscillate the inductor very small amount to stabilize the system?
And you can.
And we did it.
That's amazing.
Wow.
We did it. Now we are trying to actually bring that into wave propagation. So could we actually make some of the unstable scenarios in optics stable by just slight variation up? So we're calling it vibrational electromagnetics.
Oh, that's very interesting. I also wonder if that translates then to quantum harmonic oscillators.
Maybe,
where you
exactly,
can have these small
yes, that's right.
fluctuations.
So
In the optics case, what would you be oscillating?
exactly, we don't know that yet, but we are thinking maybe just index of refraction, very small, maybe. Again, we have to look for a scenario that is unstable and we want to make it stable. And of course, that could be also in nonlinear system. So we don't know that. We're at the beginning of this field. At least we did it for the circuits, and we saw what would happen if you change the inductor. Now we are actually working it on one-dimensional wave propagation. So if I have a transmission line and I change the L with C, what would happen? Eventually, we would like to make it for the wave propagation and in optics. We'll see how it goes. But that's another example that just a curiosity. I just became fascinated by this because I have a very interesting collaboration with a colleague, Emmanuel Fort, in Paris, that he is doing great work on water waves. We are part of a team that we studied time-varying metamaterial. So that's another area that we are working in my group. We call it four-dimensional metamaterial. These are the material that you actually change the permittivity in time. Anyway, Emmanuel Fort and Matthias Fink in Paris, they've done a beautiful job on water wave. So they have a water wave and they change this and they see how the time reversal works and so on and so forth. Emmanuel Fort has done this beautiful work of, again, inspired by Kapitsa's, that he takes this tank of water and he turns it around. So obviously the tank of water, he turns it around, the water has to come down. But then he starts vibrating this and the water actually stays. Very interesting. It's completely identical.
Can we see it in the video?
Yeah, oh yeah, he has it. He has it. I will ask him to send it to you. Yeah. And so I became very fascinated by Kapitsa's work. And I said, okay, very good. Emmanuel has done it for a water wave. Can we do it with electronics? Okay.
You're turning the world upside down.
Anyway, so
defying gravity.
It is interesting. This always fascinates me, to connect from one field to the other, to learn something new. It makes it exciting.
I have a question. So in electronics, you have the PN junction, which is kind of like, to me at least, a little bit magical. You have a system where there is a kind of intrinsic voltage, which is this very counterintuitive situation.
Sure.
You have entropy driving a energetically unfavorable situation that's like permanently that way, and I think it enables a lot of interesting. You can push against it and pull it, and so you have a lot of interesting effects. Is there a PN junction in optics, or is there kind of a direction for creating something where there's a permanent kind of strange situation that stabilizes itself?
That's a good question. I have to think about it. But maybe somewhat related to your question, maybe permanent magnet. Because you have basically magnetized element permanently. Maybe some of the ferroelectric structures that they have permanent electret, so to speak. I don't know. That's a good question. I have to think about it. Again, one of the differences, of course, in electronics, the electrons and so on, but of course, photons don't have charges. So that's...
And one thing I've thought about is there's always infrared photons going back and forth everywhere. You could have a situation where, due to some effect, one side of something gets warmer and one side gets colder, or it stays that way, or something of that flavor. Where there's a
but that would be against the second law of thermodynamics.
Yeah, sort of. Unless there's some type of entropic, unless it's entropically favorable or something.
That's right. I mean, still the entropy increases, but
somehow the entropy increases, but there's a temperature difference, or what? Some flavor of something where there's permanent imbalance.
I don't know about that part, but there has been work done by several groups looking at the non-reciprocal system in thermodynamics. But that requires some energy from outside to keep it that way, obviously, just to make sure the second law of thermodynamics is satisfied. Great question. I have to think about it. But coming back to you mentioned about the advice to young students.
Young students,
Be curious about everything. I think that's one of the, but it's very nature. As a scientist, you have to be curious. And have your curiosity expanded. Go out of your comfort zone, by the way. It's always important to go out of your comfort zone to the other field. Try to learn from the other fields. In my opinion, that's very important. Also, follow what really excites you in science. And don't be afraid of getting into new topics, which is different than what you have learned. You can always learn things. That's fine. And more, the education and learning is complete during your lifetime. It's not just you learn only in graduate school. You learn every day. And I think that's very important. And as I mentioned, expanding your knowledge, particularly as mentioned for the newcomers coming into the field, it's important that you look at the fundamental of knowledge in the field that you study, and that would help you to go into other field. And with the fundamental knowledge you have there, you can learn the other field, and then you can see the connections between them, or you can create the connections between them, and that's important. Just be courageous and go into other fields. Don't be afraid of the boundaries among the fields. Try to go across them, and by doing that, you learn new things, and that makes your research more exciting, and it can lead to interesting findings, particularly at the boundaries among the fields.
So it must be your students must be the most courageous and the most curious.
Well, it's interesting because when I interview students and postdocs in my group, I tell them I think the most important characteristics is that you should be motivated. Motivation is more important than what you know now. Because if you have motivation, you can learn things there. That's important. So be motivated about what you do. And then I tell them, when I give you an idea, if you are not interested in that idea, for whatever reason, it's perfectly okay that you tell me now. If you are not interested and you work on it because I tell you that, you don't put your heart to it. You have to be interested in the idea. If you're interested in the idea, you work very hard and you can learn and so on. If you're not interested in the idea, let me know now. That's perfectly fine. I can give you other ideas. But it's important that you be in love with the idea. And when you are in love with the idea, you can learn, you can be motivated, you work hard, and you enjoy it. After all, you should enjoy what you do. I mean, that's what really matters. After all, we enjoy what we do, and that's one of the. We are very lucky. I always tell this to my colleagues that we are very lucky. We are in a profession that we love what we do, and we enjoy it. That's an amazing thing, by the way. We should be. As I get older, I appreciate that more. That we are in a profession, regardless of the field of study, regardless of this, we are in the profession that we love what we do.
Yes, and it's a fantastic privilege to have.
Exactly.
Yes.
It's really amazing. Yeah, that's great.